So good afternoon, everybody. Once again, I'll be presenting the PPT of Chapter 4, Classification. We intend to discuss today the matrix for constructing a decision tree, right? Let me know when my screen is visible to you. Is the screen visible?
Yes, ma'am, it is.
Right. So to give you a quick walkthrough of what we have done so far. So we've spent already a couple of classes on classification, trying to define what is meant by the classification, looking at the induction and the deduction processes, the examples, and then we came over to the decision tree methods for constructing a classification model, right? So one decision tree, for example, is a model that can be used to do classification, right? So we are now in this phase, we are where we are looking at how to learn, or I can say construct a decision tree, right? So we are looking at the induction stage. So last time we, after looking at the various examples and definitions of the decision tree, we did the Hunt's algorithm, right, in detail. And in the Hunt's algorithm, please see, we had very generally, very broadly specified that whenever there are certain, we I had identified two termination uh, clauses. That is, we stop constructing the decision tree when either there are no records at all, right? Or or all the records belong to the same class. So no further branching is required to reach a particular decision, since we've already reached a decision in that case, right? But if we had mixed cases, right? So we had data and the data belonged to multiple classes, and therefore we still needed to build more levels of the decision tree to reach a particular decision. In that case, we said that at each stage we must choose an attribute to split the node. Splitting the node means splitting the data set corresponding to that particular node, right? That particular level that we are at, right? So, accordingly, we had looked at how to specify the test conditions for each type of attributes, that is nominal, ordinal, continuous. How do they vary for a binary split, and how do they vary for a multi-way split? And then we had broadly identified that homogeneity or a lower degree of impurity is what we look for. That is, we look for pure partitions. Okay, when we split a particular data set, or that means a particular node into two smaller nodes. Okay, So this is what we look forward to, because more homogeneous our distribution is, easier it is for us to reach to a particular conclusion, right? Which is the very essence of building a decision tree, right? So today we are going to see how to measure this how to measure the homogeneity or the impurity, right? So there are various measures, many more than what you see on your screen right now, but these are far and by and far the most popular ones, and used in many algorithms. Okay, so many decision tree construction algorithms, for example, mm, you can see here cart, slick, and sprint use Gini. Similarly, ID3 is the name of another algorithm that uses entropy. So these metrics, which are used to either look out for the homogeneity, we can say, or impurity. So either these measures look out for a greater level of homogeneity or a lower level of impurity, whatever. So these metrics are very popular. Okay, and that is why we are going to have a look into these. So first of all, before I start with the Gini index, let us again try and understand what do we uh, mean by employing a measure such as this. That means, uh, how will we gauge the level of homogeneity or impurity, right? So for that, please see, suppose this was the parent node that I had, which had two classes, okay? Let's say a class 0 and a class 1. These notations, please see very carefully, correspond to, first of all, the level of the node, or the node number, I can say. So parent node or the root node, let's say, is numbered as n0. Okay, so n0 class 0 ka 0, then n0 parent node ki class 1, right? These n's typically denote the number of instances, that is the number of records that belong to class 0 at node n0. Okay. Similarly, n01 would denote the number of instances that belong to class C1 at node N0. Right? And you will see that we follow the same notation throughout. So N10 here means that the number of nodes which belong to class C0 at node N1. Okay. Similarly, let's take this. So N41 would denote the number of instances in class C1 at node N4. Okay. So now what are we really trying to look here is that if we had this parent node and we did not have a clear decision here, that means this node had a very high degree of impurity or a very low degree of homogeneity. Hmm. So, and we had, suppose, two attributes, namely A and B in this data set, then whether we should be splitting on the attribute A or attribute B. To determine this, we see which will give us a better gain. Okay, gain in terms of the purity or homogeneity, right? So when I split A into, let's say, two nodes N1 and N2, then these are the corresponding class distributions at each node. Then let's say that we use some particular metric, maybe the Gini index or entropy or misclassification error or any other. So whatever metric we are using, we use that to first of all compute the homogeneity or the impurity at this level, and we call it M0, right? And similarly, after the partition for A, we compute the matrix and also for the children of B, right? And we call them as, for N1 we call M1, N2 we call M2, and so on. For Ni we call Mi, right? Then how to gauge the gain, how much gain we are having in the homogeneity or purity. So let this be together called as M12. So how to compute this M12 from M1 and M2, again we will be looking at, okay? And how to gauge this consolidated metric M34 from M3 and M4, again we will be looking, right? How to gauge the gain? Please see the gain in, we will compute the difference between the impurity at the level of parent node vis-a-vis each of its children. So M0 minus M12 versus M0 minus M34. Now whichever gives us a better gain, we pick up that attribute. So this is how we select a particular attribute. The matrix will vary. That means, as you will see in the slides now, only the formula largely, okay, of these metrics is different, but the approach will always remain the same. Approach will always remain the same. So this is what we are going to, do for each of the decision tree algorithms, irrespective of the metric. Okay, so this is the general approach. Is this clear to everybody?
Ma'am, how will we calculate M12 and M34?
Hmm. So M12 and M34 is generally computed by taking the weights of these nodes along with M1 and M2. So we will come to that. I will show you this computation in a minute or two. Okay.
Okay, ma'am.
Any other doubt? Should we proceed?
Yes, ma'am.
Yes, ma'am.
Okay. So we first look at Gini. Okay, in this series of metrics, we first look at Gini. So please see, how is Gini defined for a particular node? Gini is basically based upon the probability of a particular, of having a particular class at a particular node. Okay, so if J denotes a particular class and T denotes a particular node, then PJT is the relative frequency, that is almost the probability of having a particular class, this particular class J, at a particular node T. That means we are looking at how likely is that this particular class will be present at this particular node T. Okay, so this is the formula for Gini, and Gini basically measures impurity. Okay, it basically measures impurity. So you can see that higher the values of Gini, more the impurity would be. Okay, more impure than that particular node would be. Okay, and lower the value of Gini, lower that particular node would be. So sometimes, typically, this is a question that is asked, that what is the minimum value of Gini index, or let's say entropy, entropy that we are going to see next. It's a metric that we're going to see next. So what is the minimum value of these metrics and what does it imply? Please see, if suppose I had uh, uh, two classes, okay, and uh, uh, two classes and equal number of tuples in both the classes, then this maximum value of the Guinea would have been reached. And you can understand that this is the case where we have maximum impurity. That means we have no clear decision because there are two classes and the tuples are equally divided. So it's like people saying, half the people in my class saying we want to eat pizza, and the other half going in for a for some other North Indian dish, right? So we definitely cannot reach any conclusion, right? So the maximum value in this case would be 1 minus, as it is, divided by 1 by NC. N is what? N is the number of classes. So suppose there were, let's say, 20 classes, then each class has a tuple. Okay, so each class has at least a tuple, right? And the worst case is the case, if you remember, where we had discussed the case of a student ID, this case. So each each student belongs to a class of its own. uh, why? Because it is different, right? So we have one in each class, right? So in that case, the worst case will occur. That means 1 upon, it will be 1 upon C1 minus 1 upon C2 minus 1. So it will actually come out to be minus 1 upon NC, where NC is the total number of classes. Okay, so you need to remember the maximum and the minimum value. What would be the minimum value? Of course, the minimum value would be when all the tuples will belong to the same class, right? That would be the minimum value, and it will come out to be equal to 0, right? Let us see the computation so that this becomes more clearer to you. So suppose we have an example where there is a node which has two classes, C1 and C2, and there are a total of 6 tuples, out of which 0 belong to class C1 and 6 belong to class C2. Okay, so first of all, let us see how to compute Gini for this. So the formula for Gini is 1 minus the probability, the square of probability of a particular class at a particular node, right? So what is the probability of C1? It is 0 by 6. That is clear to you? How would you compute the probability of 0, class C1? 0 divided by the total number of tuples, that is 6, right? And C2, 6 divided by 6, that is 1, right? Now what would be the Gini? So Gini would be 1 minus 0 ka square minus 1 ka square, right? So we have it equal to 0. So you see, the minimum Gini would be 0. Okay, and that is when we have a we have all the, we have a clear decision here. Please see, or suppose there are 6 people, then all 6 people want to go with the option of class C2, right? So this is the minimum value of 0, is the minimum value of Gini, implying implying what? Implying the most information, okay, or most pure uh, mm, node, hence implying a clear decision. So this is what you are expected to write if you are asked what is the implication of the minimum value of a Gini, right? And similarly, the computation for this would be C1's probability would be 1 by 5 and C2's probability would be 5. I'm sorry, C1's probability would be 1 by 6 and C2's probability will be 5 by 6. So the Gini would be 1 minus 1 by 6 ka whole square minus 5 by 6 ka whole square, and this comes out to be similarly for this. Any problem up till here? Any problem, students?
No, ma'am.
Okay. So this is how to compute the Gini of an individual node such as a parent node individually or a child node individually. So this is how, or in other words, how to compute M0 or M1, M2, M3 or M4. Okay. Now we will see how to compute the Gini of a split. Okay. So how to compute the Gini of a split? That means when we want to split, okay, then how do we compute the Gini? For that, we also attach the weight of each node. Now, what is the weight of each node? Weight of each node is that not up till now you can see that we are only looking at the class distributions of each node. Okay, so if suppose, uh, I think I have a, yeah. So you can see that suppose this is the parent node, this is the parent node, okay, and we are trying to weigh the Gini of this particular of splitting on, let's say, this particular attribute B, where this B will produce the children N1 and N. I'm sorry, this is the parent node, and this B will produce two children N1 and N2, and uh, the in the parent node you can see there is the Gini will be maximum because the tuples are equally distributed. Okay, so how to compute this split? That is this thing M 1 2 or M3 4. Okay, so this is now what we are seeing. What we are going to do is we are not just going to look at the class distributions of these nodes individually, which we do up till this point. Up till this point, you can see when we are only looking at one node, we are just looking at the class distributions that is present at that particular node. Now what we are going to do, we are also going to attach the weight of a particular node when we compute M34. Now what is the weight of a particular node? Weight of a particular node is the total number of tuples that have come to this particular node, let's say from node B. That means we want to say that not only is this metric M3 important, that is computed from the class distribution of this node N3, but what what more is important? It is also important to look at that how many tuples out of the total tuples that were present at the parent say this, lead to this metric. Okay, so we also multiply M3 with the weight of node N3 and add that to the weight of node N4 multiplied by M4 to compute M34. Now, what is weight of a node? Weight of a node is defined as the number of tuples at this particular node divided by the number of tuples at its parent node. So you can see this here. So how to compute the Gini of a split? To compute the Gini of a split, for example, M34, we take the Gini of M3. This is M3, right? Suppose I is 3 first. So M3 into N3 by N. Okay. So I will have this thing, right? Then added with plus N4 by N M into M4. Okay, so this will give me M34. You can look at this example here. Let us make the discussion concrete with this example. So this is my parent node. How many tuples are there? 12, right? Now B is split into two nodes, and the class distributions in N1 are 5 and 2 respectively, N2 are 1 and 4 respectively. So what we do is we compute the Gini first for N1. The Gini for N1 comes out to be 1 minus 5 by how many tuples are there? There are 6. So 5 by 6 ka whole square minus 2 by 6 ka. This should be 7, I think. This should be 7. There are a total of 7 tuples here and 5 here. I think this should be 7 here and 5 here. Okay. So we compute the Gini. 1 minus this 5 by 7 ka whole square minus 2 by 7 ka whole square, whatever it comes out to be. Gini of N2 is equal to 1 by 5 ka whole square minus 4 by 5 ka whole square, right? And then how do we compute the overall Gini, that is M34? How do we compute? Please see. What is the weight of this node? It will be 7 by 12. And what is the weight of this node? It is 5 by 12, because there are 7 tuples here. There are 5 tuples here, right? So 7 by 12 into whatever this value was, and 5 by 12 whatever this value was, plus this. So this gives me this. So this is the Gini of the split. So similarly, we compute for A, and then we see uh, we subtract the Gini of B from 5. What do we get? 5.5 minus 0.333. So whatever we will get, we will contrast this with the Gini of the parent minus Gini of the split on A. Okay, so whichever is greater, we pick that particular node. Any problems here?
No,
Is this
ma'am.
clear?
Yes, ma'am.
Right. Now, suppose, see, up till now we have been assuming that these are all binary nodes. That means there are only two classes, C1 and C2. Okay. Now, suppose we had more than two classes. That means suppose that our attribute was categorical. Okay. Either nominal or ordinal, any, right? How would we then compute these metrics? So the idea is simple. Here we are computing for each class. There each we would again, we will again count the number of instances for each value in a class, and then we will compute the Gini. So same thing actually, only that here there are only two classes. Here it will increase, right? Then what about the continuous values? In for the continuous values, please see what we do is, for example, we had that taxable income example that we saw. So cheat no, and correspondingly, this was the taxable income. Okay, now what we have done is we have divided the taxable income into these are the actual values. Okay, and we suppose certain values ourselves now. Okay, now what we do is we keep on scanning the data. For example, this is the data. Okay, so as soon as 125K comes, we go and we uh, greater than 122, we yes, we, and if it is a yes, then we up the count of yes. If it is no, then we up the count of no. So greater than 122, we've chosen these split points, and we come here and we increase the count by 1. Then 100K no, 100K no. So we greater than 97. Okay, greater than 97, we come here and we no, we increase the count by 1. So this is how we get yes, no, yes, no. This is how we get the counts, and then we apply our normal formula. Okay. Now, what you need to do is that you need to practice. So there are questions at the end of your book. I will also try and look for a solution manual, or uh, if I don't get the solution manual, I'll pass on the uh, I'll pass on a couple of solved numericals. I'll do send them to you so that you can practice, okay, these with your own hands. So these are very easy marks, but then you get numericals based upon these. So you may get how to construct a decision tree, for example, based upon, they will tell you the metric. So based upon Gini, based upon entropy. Okay. So these are the generally two metrics which are get most probably asked. The next metric that we're going to look at is entropy. So again, as I told you, only the formula largely is different. Uh, Now, in this case, again, the minimum value is again 0. Again, implying it happens when all the records belong to the same class, and implying the maximum information. And the maximum value in this case, so you can take a small example and you can try computing it. You should verify this, so it will come out to be log of NC. The other things are the same. PJT is the again the relative frequency of a class J at a particular node T. Okay, and the entropy based computations are similar to the Gini index computation. So this is what I told you earlier. Let us we can also look at an example to make our discussion more clearer. So again, the same example, if you see. So for class again, we compute the probability of class C1 and C2 at each node, and then we put it into this formula. Okay, so you need to work out these examples with your own hand. That is it, right? Now, please see uh, how to uh, compute the information gain here based upon entropy. So again, you see that entropy, the split is the gain on split is computed just like the gain in Gini. So this was the formula that we were using there, right? And actually we were subtracting. So you can see that gain. This is how gain is computed. Whether our metric is entropy or uh, uh, Gini, right? So to and even the formula for computing the entropy, mm, metric for split. This is known as the metric for split. In beginning, is similar to what is the formula for entropy, but there is a little difference here. That little difference is that now here we don't just compute the gain. In Gini, we were stopping at computation of this gain only. Okay, so if you remember, this is how we computed M1, 2, and M3, 4, right, in Gini. And after that, we computed M0 here. So after this, I told you we will compute M0 minus this, right? But we stopped there. We stopped at the gain, right? But now in entropy, we go a step further and we also compute gain ratio. So what is this gain ratio? Gain ratio is basically this gain that we have computed. That means the entropy of the parent the entropy of minus the sum of entropy of all the children divided by split info. Now what is this split info? So split info basically tends to penalize the higher number of partitions. What this means is that Gini is good and so is entropy. But if we just look at these metrics or up till this point where we are computing gain, we the disadvantage that comes out to be is it has been seen when these algorithms are run that they produce a very large number of partitions. So the entire focus so far in these algorithms have been on computing a pure partition, right? At each step, what are we looking for? We are looking for increasing the purity, increasing the homogeneity, or decreasing the impurity, right? But that sometimes results in a very large number of partitions. Each of these partitions are pure, but the number of uh, mm, branches become very large. So, as a result, you can think what this means is that there are a very large number of rules that you will get from the decision tree eventually. Each rule is formed when we traverse from a root to a particular leaf. Okay, so every time there is a new branch created, we add a rule to our database. Okay, so to reach a particular final conclusion, you have to go through all those rules, right? So larger the rule base, obviously larger the time taken, right? Now, to somehow reduce the number of partitions, that means to impose penalty on a very large number of partitions, what we do is we divide it by this quantity called the split info. And what the split info tells us, it is the actually if you see this is the what is this ni by n? This is a metric which is computed based upon the number of children of a particular node. What is Ni? Number of children of a particular node N, right? So we divide the gain. We say that this gain is not the only thing we should be looking for. When we compute gain ratio, we divide this by the split info. Split info means the number of partitions that were done from a particular level. Okay, so for each level I, you can see that it is computing this ratio and it is summing it. Okay, so and the larger this number is, the smaller the gain ratio will start becoming. Okay, so this is another thing that we compute. So this will let us know whether the right subtree is better or the left subtree is better, right? So this is another thing that is introduced in the entropy. Then the last metric that we are going to look at today is the classification error. This is the formula for the classification error, and again its minimum value is 0 and the maximum value is just the same as the Gini. Okay, and the implications are also the same. So minimum is when all the records belong to the same class, uh, and maximum is when the records are equally distributed among all the classes, right? This is the computation. So you need to work this out yourself. Okay, apply the formula. So uh, this is a simple example, although this is not asked, but if you are given the same data, they may ask you to compute Gini and also compute misclassification error and tell which one is better. Okay, so whichever is lesser obviously will be better. Okay, so this is what you have to do. Now, tomorrow's class, I want to introduce some metrics to measure the efficacy of a decision tree. So we will see how to evaluate the performance of a decision tree. Okay, so this is what we will see in the next class, and we will finish this chapter also. Is there any problem in today's class? I request you to just wait for 2 minutes. I'm sending the link for the attendance. Thank you, Kajal. Thank you for your input.